Okay. So what we're gonna do today, okay? What we're gonna do today is that first we're gonna talk about some topological spaces, or so to say, the definition of a topology. So this is the first topic, topological spaces. And this is the definition. Let X be any set, and let's call some tau, which is defined as some UI. This UI is I'll explain in a bit. These are also called index sets. So what this J is, this tau is, you can think of it as a family of sets which consists of some UI, and in fact they are a family of open sets. So this tau, it will denote a collection of subsets of X. Then the pair X comma tau is called a topological space if tau satisfies the following. The first condition is that your null set and the set X, it should belong in tau. The second condition is that if tau is any subcollection, and this subcollection, it might be infinite as well. So might be infinite as well. Subcollection of I, then the family UK, where K is some index, and this is just your index set, the capital K, satisfies oh no, I started on the last page again. Okay, so this family of set, it will satisfy the following requirement. This is a, this is an intersection symbol, or so to say the cap symbol. You can think of it as, let's say, this capital set K consists, let's say, 0, 1, 2, suppose. Then this guy over here, the thing you see, it's nothing but intersection of U of 0 intersection with U of 1 intersection with U of 2. Okay. And there is another requirement. Oops. Sorry, it shouldn't be intersection. We are calling this infinite, right? So yeah, it should be union. Sorry about that. Intersection is another condition. And these are also called arbitrary unions. It should be union, okay. Big U or something. Sorry about that. It shouldn't be intersection. So if you're confused, you can ask. So the second requirement says that, okay, you have some set X, and you can have some subsets inside that set, and those subsets have to be open, and if they're open, then their arbitrary union, it is open as well. That's what the requirement 2 tells you. Is that okay? If you have any questions, you can ask. Okay, so moving on to the third requirement.
Shouldn't
Yeah.
those be unions then? U0 union, U1 union.
Yeah. Yep. U2 and so on. Okay. Anything else regarding this condition number 2? Any questions?
What does infinite mean, like in this sense?
In this sense, those sets, the family of sets, we don't usually say infinite. Nakahara told it like he expressed this thing as infinite, but if you consult Moncrief regards this as arbitrary union. So it should be countable, but there can be many, like a lot.
Oh, so infinite refers to the number of unions you're making.
Yeah, so when you write something like this, let's say this runs from I to n of some ui. This is u1 union with u1, union with u2, union with u3, so on. And this n can, can tend to infinity as well. That means you have infinitely many open sets that are labeled by some index, some u1, u2, u3, and so on. And the fact that arbitrary union of open sets are open, if I recall correctly, you can prove this by using De Morgan's law. But we are not going to prove that in this course. So yeah. Anything else?
No.
Okay, so now for the condition number 3, or the requirement number 3. Now if I have some finite subcollection of I, that means again I'm taking some subsets, but this time instead of taking infinitely many, I'm taking some finite ones, like let's say u1, u2, u3, and so on. So if I write, if K, capital K, is any finite subcollection of this family I, and this I, you're seeing this as an index, right? So you may ask, okay, we are calling it an index, so why we're calling it a subcollection of I? Well, I is an index, so I, let's say, run from 1 to 10, suppose, and we are taking a finite subcollection of I. So what we mean is that we are taking, let's say, u1, u2, and u4. So that's a finite subcollection of I. So sometimes people even call it an index family or indexed family. So that's why this term is here, like a finite subcollection of I. Don't confuse this capital I with some, sets and stuff. They're just indices. That means all the indices actually come from this I thing. That's all. Okay, so let's take a finite subcollection of I, and the family is given by the family of sets is given by some uk, where small k belongs to this capital K. What it means is that if you put some index, then the let's say you put k equals to 1, then u1 should belong to your subcollection capital K. Satisfies the following requirement. That means this finite intersections of your sets, this will also belong to tau. If any type of set, some set X satisfies these three conditions, then we call that set as a topological space. Sometimes we call this tau as the the topology over the space X. So what it does is that this subcollection, or so to say, this collection of open sets, they give a topology over the set X. And all the U's that you see here, they have to be open sets. So if I summarize these three, very crude points, is that I have some set X. Inside X, I can have some open sets that are denoted by U1, U2, U3, U4, and so on. The first condition that we see is that the null set and the set X, they have to belong to tau, and tau is a collection of open sets. So all the open sets you can make, you are making a collection of them, and that is your collection tau. Null set is open for now. If you dig deep into topology, you can actually show that null set can be open and closed. So you can use that piece of information to your advantage. So null set is open, and all the sets are that you make a collection, that is this collection of U1, 2, 3, whatever you want to call them, they're also open sets and they belong to tau. The first condition is trivially satisfied, which is phi and X, they belong to tau. And then what you say is that if I take the arbitrary unions of these open sets, which are subsets of X, they also have to belong to tau. And then you talk about the finite intersections of open sets, which is also open, and they have to belong to tau as well, because from the very beginning we constructed tau as a collection of open sets. So this is the summary. We have some collection of open sets. Open sets in X, which we call tau. Then phi and X has to belong to tau. This is the first condition. Second condition is that arbitrary union of open sets, which are subsets of X, they also has to belong to tau. And then finite intersections sets, they also have to belong to tau. And if you can get a collection like this over some set, then what we say is that tau, or those collections of the collection of open sets that we gathered, this tau will give some topology over X, or some people even call it the topology of X is tau. This is the definition of a topological space. Okay, is that clear, the definition? Okay, so questions?
আমার একটা কনফিউশন হচ্ছে ওপেন সেট তো এভাবেই ডিফাইন করি আমি, এই যে যেভাবে জানি আর কি, যে টপোলজির ভিতরে থাকলে হচ্ছে সেটা ওপেন সেট, আর না থাকলে
That's another way of saying, because the very collection is made out of open sets, right? I think you're talking about markers. Yeah, you can do this the other way around as well. If your set belongs to the topology, it's an open set. And by topology, I mean this collection tau. But ওটা তো আরো পরে আসে. First, you have to, you have to define your open sets, and then you can get a topology. Or if you say, oh no, I have some topology, and I want to check whether some set, let's say x, small, like x prime or something, whether that's an open set or not, I can, check it by comparing that set with my collection of open sets that defines a topology over some space x. Okay?
হ্যাঁ
বুঝতে পারছো?
হ্যাঁ বুঝতে পারছি।
It's just the other, what you're talking about is just the other way around. Okay? It goes both ways. Okay, so
Sir, I have a question.
Yeah.
So the x yes, the x, I mean the t মানে tau is the collection of all arbitrary collection of a set whose arbitrary union is also inside set, and finite intersection is also inside the set tau.
Tau.
And the x itself and empty set is in tau. So tau is the topological space of x. Is that correct?
Yeah.
Tau is the topology. X and tau together are the topological space.
Yeah, but people often call it like tau gives a topology over x, and formally you have to say this collection is some topology. This collection is some topology. Tau is a collection of open sets, and those open sets give a topology over x. Okay?
Okay.
Okay, so now let's look at some examples of topology. These are pretty trivial examples. Then, okay. Which one should I tell you first? Let's take an abstract example. Let's say x is some set. And tau, which is a collection of open sets. Tau here is all the, is a collection of all the subsets of x. So can you understand that if I put this condition, the fact that tau is a collection that collects all the subsets of x, that will introduce a topology over x? It's pretty easy to see, because you can first say that, oh, I don't have any idea what x is, right? So how can I determine the subset? So what you do,
basically tau এদিকে পাওয়ার সেটটা
let's not talk about let's not talk about power sets. Let's just stick to subsets and stuff. So if tau is a collection of all the subsets, take a very discrete example. For example, this one, 1 2 3, or even 1 2, I don't know. So can anyone tell me what are the subsets? That means if I want to have a collection of subsets,
Empty set 1,
empty set 1
2,
2
And 1 2.
1 2
1 2. So from this collection you can see that phi and x is what, 1 2, right? They belongs to tau, right? And take their arbitrary union, that also belongs to tau, right?
yes.
And take their finite intersection, do they belong to tau?
Yep.
Okay, so all the three conditions are satisfied. So if you have a collection of subsets, where you have some, bigger set X, and all the subsets are inside tau, then that will give some topology over X. Or so to say, we can say, oh, X is a topological space. And this type of topology is called a discrete topology. This is one example of this, topology. You can even have topologies like this. Let's say for some set X, your tau only consists of the null set and the set X. And you can easily check that it will also satisfy all the three requirements. And this type of topology is called a trivial topology. Then if you consider, let's say X, if we consider X to be the real line R, then all the open intervals which has a form of A comma B and their union define the usual topology. These are just names, okay? So by this condition, you can prove that, oh, this X, which we are identifying as the real line with some open intervals and their union, it will satisfy the three requirements, to be the topological space. And this type of topology is called the usual topology.
Is this also called the standard topology? Because I heard that name somewhere else.
I cannot recall right now. I have to check Montres for that.
All right.
There was this usual topology, the standard one, the trivial one. I don't remember about the standard topology right now. I think someone texted something. Wait. The naming of discrete topology, does it have anything to do with discrete metric? At this point, no, I don't think so, because when we are defining these sets, you see that there was no notion of distance, right? So if there is no notion of distance, I don't see any point why should we consider anything about a metric, even though I might be wrong, I don't know. But that's how I understand it. Since we are not defining any sort of distance, or we are not concerned with any sort of distance, so I don't think so. Like the distance has to be discrete and stuff like that. But I'll look it up, okay? So metric spaces are very special cases of topological spaces. Topological spaces doesn't necessarily have a metric unless you define a metric on it. That's why I said in the previous class that geometry cares about distance, topology doesn't.